I know you have it in you to be great, but today we're going to be great. Again, I'm going to take a minute to check uniform, make sure everybody's playing by the rules. While I'm doing that, I'm going to have you do one thing for me. I'm going to give you an equation, and I want you to figure out the special symmetries of the equation. Use your notes if you need to, that's fine. But let's go through, have you and your partner go through the special symmetries for this equation. Alright, so there's your equation, and our special symmetries, remember, are in any order: x-axis, y-axis, identity, and origin. So remember the tests and go through and do that while I
Well, she just wrote it up there. I just wrote it on the first, yeah.
There you go. You don't have a ticket. I have no idea.
Will that be
Or
different
I
for each
completely without. No. Keep working on that. I'm gonna email the person in charge. So you keep working on your math. That's your job right now. To get the ticket, yeah, you don't have to have a full amount.
You own the equation. Yeah.
Wait, that's right, church uniform. Yeah. All I know is on Thursday?
You can either wear your college stuff or spirit wear. But
No, on Thursday.
seniors can. You can wear either. You can wear spirit wear
That's in college.
or spirit wear.
Yeah. Where have you done it for the fundraiser? For the fundraiser.
Well, yeah, but he doesn't have a fundraiser dress down.
I wore this like 10
It's
times.
fine, but today you're busted,
Okay.
okay? You can't be out of uniform unless you're allowed to be out of uniform.
No, I thought seniors would ever wear college
No.
or spirit wear.
No. Seniors do college stuff, and then on Fridays, they go to their work. Okay? You're busted.
I think it was.
Alright, who else is gonna ruin my day? Sam?
Yeah, I have to say you
I do.
Where is it?
Right here. It just broke last class, and I can't get a plastic. It's going to break last class. I've always seen it that way.
Why's your posture so good?
I have to go to the board.
Am I doing the uniform?
You're on.
Yeah, and you still have to realize
You're on here, so it's good.
Vanderbilt lost like 50 points.
Yeah,
I'll take it. Wearing something like that, you know, I can't. You got done. It was a player.
It wasn't funny until
He like a good team. And then they were like,
Alright, did you do your test of symmetry?
The x-axis first, or what is it?
How do we test for the
You
x-axis?
change it on the y, and the
Change
y.
the sign on the y.
And y would work this
And
way.
y would work because we're gonna gonna square that negative out, right? So hopefully you said yes on that one.
X1 or Y-axis doesn't work.
This is gonna work because we're changing the sign on X, and that's gonna turn that into a plus, which isn't the same equation, so that one is a no. Remember, after you do whatever you do, plug in whatever you're plugging in, it has to end up matching the original. Exactly. Identity, this one is easy, because when we switch our variables, it's not gonna be the same equation. And if we change both signs, that's the origin test, this part works out okay, but that one doesn't, right? Everybody got that? So the only symmetry this one has is to the x-axis. What? What x-axis? What's even? Y-axis. Y-axis is even. So if this were one of those, is it even or odd or neither question?
Neither.
This is the even test, and this is the odd test. Okay? Now, we talked yesterday, saw some examples where, can you have all no's? Yep. Can you have more than one yes? Yes. So you just have to do each test to see what you got. Okay? All right, next. That was a little review. Now we're actually going to number 7. I'm on page 12, number 7. And we're going to identify the type of discontinuity. Okay? Now, a discontinuity is something that breaks your graph into pieces. Okay? Never continuous, I can draw the whole thing. If I'm not continuous, there's something in there that's breaking it apart. And the types of discontinuities that we're going to concern ourselves with are called removable, E in there, or is that just
No, there's no.
removable, and non-removable. Graphically speaking, I'm going to tell you this, and we're going to talk about how you get it. A removable discontinuity graphs as a whole in the picture. A non-removable discontinuity graphs as a vertical asymptote. Okay, how do I tell from the problem? Well, if you look at the first one, do you notice that you can factor the top? So if we take an x out of the top, we would have that. And then what do you notice? You can
Simplify.
cancel or remove the x. So what kind of discontinuity do we have here? Removable. We can cancel it out of the problem. Now, it doesn't disappear totally, it just means I'm gonna have a hole in my picture. But it's a hole, not an asymptote. So when I draw it, it might look like that. It has a little open dot in it. Now, look at the next one. Is there any canceling that can happen in this problem? No. So this problem is going to have a vertical asymptote at 2. Because what happens if I try to put 2 into the problem? I get a 0, and are zeros allowed in the bottom?
Absolutely.
Yeah. My favorite math week shirt, on the front it said, it's all fun and games, math, it's all fun and games. And then on the back it says, until someone divides by 0. Isn't that cool? Isn't that cool?
like that.
Favorite math t-shirt of all time. When I was in my old classroom, I had them on, I had them hanging up on the walls. My favorite one of all time, years ago I taught IB, we used to have IB here, International Baccalaureate, and I taught that math. And that year, one of the years I taught IB, we were putting together a math big t-shirt, and the kids brought me an idea, and I thought it was awesome, but everything has to be approved. So I took it down there, they wouldn't approve it. All right, so I was like, dang, okay, so we had to do a different one. Well, these kids, I had it for 2 years in a row, and they surprised me on the last day of school. They had this t-shirt made, they actually had it made for all of them, and me, I have one. On the front, the black, with big white writing. On the front it says, got math? You know how the old got big question mark? And on the back it says, you bet your ass some totes. Isn't that cute?
I wish we still had those.
That was bad.
I'm pretty sure one would have those missing.
That year, every graduation party I went to, I wore that shirt. I was so proud of it, it was so cool. And then I had it hanging in my room, but when I hung it in the room, I could only show the side that said, got math. I couldn't show it.
She works school.
All right, here we go. Even, odd, or neither. Here we go. Even, odd, or neither. So remember, this is half the work of the one you did a minute ago. Because the one you did a minute ago, you did 4 tests. For even and odd, you only have to do 2. Okay? So we're going to do a test for the y-axis. If I change the sign on x, if I change the sign on x, will I get the same equation?
Yeah.
Yes. So is this even? Yes, it is even. Now, let's check to see if it's odd. Remember, they can be both, depending on the equation. The origin, that would be negative y and negative x to the 4th. Is that gonna work? No, not odd. So this is just even. Okay, how about this one? So y-axis. What happens if I change the sign on my x? Will that work?
I think it'll work.
I think you're right. So this is even also. How about if I change the sign on both? Remember, this is y. That's the same as y. So negative y. And we talked about last time that if you can tell, after you keep practicing, getting better and better, you don't have to show every single step. Because you can see this isn't going to work, is it? Because that negative is going to cancel out, but this one isn't. So that one is not going to work. All right, would you do C, D, and E with your partner? And then we'll compare notes on that. C, D, and E. You're only doing y-axis and origin. We're only testing for evenness and oddness.
I got it.
I'm just gonna guess because it's
Oh, you left.
For D, did you get odd? Well, she just said she did get odd.
For C, I got odd. Now, there's a lot of signs going on in this problem, SIGNs, but I got odd because when I made this negative y and I made these negative x's, this actually becomes negative 2x cubed plus 3x. So when I divide that negative out, I go back to being positive 2x cubed and negative 3x. Does that make sense, or do I need to rewrite it and spread it out? It's okay?
Yeah, wait.
All right. I got this one to also be odd. This was a little easier. Wasn't even. But when I changed the sign on both, wouldn't those cancel out?
Yeah.
So that is another odd.
For a question, will it always be either or odd?
No, it can be neither.
The last one.
So I got neither for the last one, actually.
I don't know what I did, but I got neither for C.
Well, when you change the sign on y and x both, you have negative y equals negative 2x cubed. These don't, that's a negative x cubed, so that's gonna be a negative. And that's gonna become a positive. Then when you divide the negative out, that becomes positive and that becomes negative, which is the way it is in the original. One thing here, these negatives don't cancel. That one gets squared out, so it's still negative. But I didn't do it. I got a neither for the last one. We okay? You get neither? Alright. One more section, and then we're done with 1.2. We are gonna find all of the asymptotes. Stop yawning. The asymptotes that we're going to find right now are going to be horizontal or vertical. There are things called slant asymptotes. We're not getting into that right now. We're just vertical and horizontal. So, I'm gonna look at my first problem. Nothing will cancel. The denominator is problematic because could x be negative 1? What happens if x is negative 1? I get a 0 in the bottom, and I'm not allowed to have a 0 in the bottom. So this one has a vertical asymptote at x equals negative 1. Vertical asymptotes are cannot be's. What can x not be? Well, x, in this problem, x can be 0 because I would get 0. The denominator can't be 0. The denominator can't be 0. Vertical asymptotes come from the denominator. What makes the denominator 0? That's your vertical asymptote. Okay? someone says what are the vertical asymptotes, your beady little eyes go right to the denominator. Now what about horizontal? To find a horizontal asymptote, you box in your variables, box in the x's. On top, I have 1x, and on the bottom, I have 1x. 1 over 1, my horizontal asymptote is y equals 1. 1 over 1. That's how you get the horizontal. The vertical comes from the denominator. The horizontal comes from the box. If this had been a 2, then it would be at y equals 2 over 1. Yes, I did that. You did this last year.
Never mind, I got
If
it.
the 2 were switched, then it would be 9, right?
No, it would be
Don't
1
need
half.
to beat around the bush. It'll only
It's
be nine.
x over x. So 5x over 7x would be 5 7. 8x over 13x would be 8 13. Okay?
What if it was like undefined?
Let's just wait a second. Let's just one step at a time. How about B? Tell me about B. Where is the vertical asymptote in B? X equals -3. Make sure that you are using letters. Half credit if it's just a number. Your vertical asymptote is x equals -3. Because vertical asymptotes come from the denominator. Now, box in your x's. You have 2 over 1. So your horizontal asymptote is y equals 2. What about C? There's no asymptotes in C. Let's talk about that. How do you get a vertical asymptote? You have to have a denominator. No denominator, no vertical asymptote, period, okay? How do we get a horizontal asymptote? Well, we have to build a box, but I guess I would have to put a 0x squared in the bottom. And what's 1 over 0? 0. No denominator means no asymptotes ever, okay? So if you don't have a denominator, you're not gonna have any asymptotes, period. Unless you're something with a tangent or something like that, okay? All right, how about D? Caitlin, this may be what you were thinking of. Let's look at D. Does it have a vertical asymptote? Joe?
Does the vertical asymptote be plus or minus 1?
All right, let's talk about that. What do I get, Joe, if I put 1 in here? If I put 1 in, does it work? Can I get an answer?
Yeah.
Yeah, so that's not an asymptote. An asymptote is a number you put in, put -3 in, and you get 0. Oh, what did you say, Elijah? You can't get 0. This has no vertical asymptotes because that denominator can't be 0. Think about it for a second, guys. Can you square and add 1 and get 0? Won't you be positive? Yeah. So there's no verticals. Good job, Elijah. Great work. Now what about a horizontal? It will be y equals 0. Because, guys, how many x squares do I have on the top? 9. So when I box in my x squareds, I get 0 over 1. No x squared, 1 x squared, 0 over 1, which is 0. No, y equals 0 is an asymptote. None means in my picture there are no vertical lines. Y equals 0 is right there. There is an asymptote right there. How about E? No vertical asymptotes in E. This is Elijah's problem all over again. Look at the denominator. Come on, you guys gotta think. You're smart. Look at that denominator. Can it ever be 0? So that, exactly, and it's squared plus 1. If it were squared minus 1, then you could do it, but not if it's plus. So, no verticals. Does it have any horizontals? Y equals 1, because it's x squared over x squared. Remembering this from last year? X squared over x squared. Okay. How about F? Now I need you to be really careful with F. It's starting to get tricky here. What do you notice about your numerator? Your numerator can factor. Now why is that important? Because now I can cancel. So I will have a hole in my graph. A hole. We're going to find out what it is in a minute. But before we do that, guys, let's rewrite our problem. Isn't this all I'm left with now? Isn't that all that's left? Does that have a denominator? No denominator, no asymptotes. So there's no vertical asymptotes and there's no horizontal asymptotes. But there is a hole. So there won't be any dashed lines in this picture, but there will be an open dot. Here's how we find the hole. You canceled out x plus 3. If you hadn't canceled it out, you would have an asymptote at -3, right? That's where your hole is. Your hole is where your asymptote would have been. Then, you gotta find the y. So you come down here to your new equation, and if you have x being -3, y will be? What's -3 minus 3? So we just plug in our x value. You're cruising for a bruising, buddy. -6, that's where my hole is. So when I graph this picture, I won't have any dashed lines in it, but at -3, -6, there will be an open dot in the picture. Okay? Try the last one all by yourself. Or you and your friend. You and your partner. Try that last one.
Oh, yeah.
Okay, Keller, my man. You need 150. You need 150 for Smith. I just got the word from Mrs. Smith. So I'm not going to write you detention because I think you didn't pay attention and you thought it was 125. It's starting tomorrow. I'm going to email all your teachers or Alpha anyway. Or Alpha Maria. Okay, so get 25 more bucks in there.
Did I get attention?
You're getting an infraction because you're not uniform.
But no one has ever told me that. Like, no one, I've pointed like 5 times and no teacher has ever told me that.
And I'm equally guilty with all your teachers. It's sweetheart. Are you breaking a rule?
I didn't know it was
Okay, if you're speeding, sometimes they catch you, sometimes they don't, right?
I get an infraction.
You get an infraction. One infraction. Huh? Paper towel. All right, are you making progress with this? Tell me what you did first. I hope you factor.
Oh,
How did the bottom factor?
X plus 5.
X. So what did you notice? We have a hole at the point where X is what? Where the asymptote would have been, and the asymptote would have been at 4. How do I find the y coordinate? It's a point. Plug it in right here. So if I plug in 4, I'm going to get 8 over 2. Do I have any asymptotes? So my vertical is x equals 1. And my horizontal is y equals 1. There we go. We okay with that? All right, that takes care of 1.2, so that homework will be due on Monday.
Just 1.3
Notre Dame.
To do 1.3, we're gonna start with our BFFs. Today, we're gonna start with our BFFs. They are included with the 1.3. Okay, but we can't start the actual notes until we go through the BFFs. Basic family of functions. Okay? Basic family of functions. Now, notice there's a lot here. Look at all this stuff. We're not going to answer every one of those questions for every one of these because it'll take us forever. We're going to talk about, we're both going to go through one of them, we kind of already talked about it, and then you can figure out the other ones as needed. So if somebody says to you, is the quadratic function increasing or decreasing? I don't want you to memorize that. I want you to be able to figure that out. So in order to do that, we have to know what these things look like. So the identity function is the equation y equals x. See where it says y equals right there? Y equals x. It's also sometimes called the linear function because its graph is that perfect 45-degree diagonal through the origin. Okay? This one's kind of boring, so I'm not going to run through all that. I'll run through it when we get to a more interesting function. All right, the squaring function, also called the quadratic function. Squaring is also called quadratic. And its equation is y equals x squared. And what does y equals x squared look like? A nice little parabola. Make sure your parabola is curvy, because in a while we'll be talking about the absolute value, and that one is a v. Alright, so let's run down through, this one's a little more interesting. Let's run down through some of our vocabulary words and make sure we understand. Domain. Those are the x values. So what x values are graphed up here? All real numbers. So we're going to write that like math students, negative infinity to infinity. Now what about your range? From 0, and actually that should be bracketed from 0 to infinity, because this graph doesn't go all the way down. It only goes down to 0. So from 0 up is my range. Does that make sense to everybody? All right. Now we have continuity. Is this thing continuous?
Yes.
Can I draw it? Yep, there's no asymptotes and no holes in it. It is continuous. Is it increasing or decreasing? Both. Somebody said both.
We don't say so. We don't say that.
Remember, increasing and decreasing is always a description of left to right. Left to right. So if I start on the left and start moving, my pencil is going down. So I am decreasing from negative infinity to 0. This whole part of the graph, these are x values. I am decreasing this whole half of the graph. But then what happens when I get to 0? Then I start increasing. These are x values. Don't look at the y's, no one cares about them. With this word, increasing, decreasing, look at the x's. Symmetry. Y-axis. So this symmetry is y-axis. Now, if you were unsure, I think when you have that picture, it's kind of clear that's the axis of symmetry. But could you do your tests on that equation? You sure could. If you put in a negative x, it's going to be the same thing. You have symmetry about the y-axis. Good. Boundedness. Bounded below. You are awesome. Bounded below. And where is it bounded below? At y equals 0. That's right. It's bounded below at 0. That's the floor. The floor is 0. There's no upper bound. There's no ceiling on this guy. Right? Local and absolute extrema. Now, guys, this is hard to know. I don't need to make it hard. Let me show you kind of what's going on. This is a different picture, but let's look at this one for a moment. This picture, actually, this picture has a local maximum. This is called a local maximum, sometimes also called a relative maximum. Relative and local are the same word. So this is a local, and this is a local max. What a local max is the top of a hill. If you have a hill in your picture, you're going to have either a max or a min, depending on which way you're going. So there's your local max, there's a local max. Of those two, this one is also an absolute max. What do you think that means? It is the highest point on the graph. Sometimes also called a global max. I'm sorry about all the different vocabulary, but we have to know it all. So, both of them are locals. This one, there's only one absolute, there's only one highest point, and that's this guy right here. All right, now let's look here. What do you think this is called? A local minimum. Is there an absolute minimum? No, because this thing is going down forever. Hills and valleys are what we call your relative extrema, your high points and low points, maxes and mins. If arrows are involved, that's not a hill or a valley, that's no, you don't have anything. So, local max, local and absolute max, local min, no absolute min, okay? Now, do that with your picture. What do you have here? You have no maximums. You do have a minimum. You have a relative or local minimum and an absolute minimum at this point right here, right? So where it says local extrema, you have a local min at 0, 0. Where it says absolute extrema, you have an absolute min at that point. Because it is the very lowest point on the graph. One more time. Your locals are going to be tops of hills, bottoms of valleys. Your absolute is going to be the very lowest point on the whole picture, or highest point on the whole picture. Okay? Horizontal asymptote. That guy have a horizontal asymptote?
No.
No. Vertical asymptote? No. By the way, this is your equation. No fraction, no asymptotes, right? There's no asymptotes in that picture. And behavior. Okay. Now we're going to write this. I'm not sure how you wrote it last year, but this year we're going to write it like real math students, just so you get comfortable with this kind of notation. Okay? So this is how you're going to write it. You're going to write LIM, that stands for limit, LIM. Underneath it, you're going to say as x approaches infinity. And then you're going to repeat, limit. Only this time you're going to be approaching negative infinity. Your end behavior is this. What happens out here? So the limit as x approaches infinity of my function, which is x squared. Now I want you to notice how that's written. If this is the line on your paper, those are on the same line. And this guy is right below. Okay? This is how it has to be written. Now, ask yourself, as x gets bigger, this is to the right, I'm going to positive infinity. What are my y's doing? As I go to the right, my y's are going up. So I will say positive infinity. Isn't that where my y's are going? Arrow. Arrow. Up, 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 up. Now, what about as I'm going to negative infinity? It's still going up. So this is what we call an up-up function. Both ends of the function are going up. That is true of every function where this is even. So if this equation had been x to the 4th, it would be up, up. X to the 6th, up, up. Now, there will be some other stuff in the middle, but the ends will be up, up. Okay? Mr. Delaney, please. All right, let's look at the cubing function. Let's fight through this, guys. Let's fight through one way. The cubing function. The cubing function is y equals x cubed. We're going to answer all these questions. Stop it. For the cubing function. Here is the picture. When you draw a cubing function, you have to be very careful. You start just like you were going to draw a parabola opening down. That's how it feels. It feels like I'm drawing a parabola opening down. But when I get to here, to the origin, then I draw a parabola opening up. So half is down and the second half is up. This is not a line. It has a squiggle here in the middle. A squiggle. That its domain? Everything. Beautiful. What is its range? Everything. You guys are good. Is it continuous?
Yes.
By the way, if we're not continuous, we would say no, and then we would say something like, there's a vertical asymptote at x equals 2, or something like that. So we're specific about where the discontinuity is. Okay, increasing or decreasing? It is increasing. Look, left to right, guys. This is left to right. Okay? Which way is my pencil going? Up the whole time. So we are increasing on the entire domain. We are never decreasing this function. So how far, this picture, how far to the left does it go? How far to the right does it go? That's domain. Domain is your x's. Which x's have you graphed? You graphed all. We also graphed all of the y's. Does this guy have any symmetry? This is a little trickier. What? The origin. In this is an odd function. It has symmetry about the origin. It has symmetry about the origin. That is the only symmetry it has. Now, I'm old, I do this for a living, so I can look at that picture and say confidently, that's the only symmetry it has. If you're not so confident, what could you do? Do the test, right? You can do the test. Changing x, y, whatever, and see if any of them work.
Is there no bounded?
Is it bounded? Is that my next one? Is this guy bounded at all? No. No, not bounded at all. What's the clue? Arrow going down, arrow going up. No ceiling, no floor. Local extrema, all right, back up. You heard me say, and I'll say it again, local extrema are tops of hills, bottoms of valleys. We don't have a hill or a valley, so therefore we have no extrema. And if you have no local extrema, you're sure as heck not gonna have a absolute horizontal asymptote. None. Remember, a horizontal asymptote is something that the curve approaches. This is not approaching anything except infinity, right? Okay. How about a vertical asymptote in that picture? No. End behavior. So again, guys, this is how that's written. Every single time you do an end behavior, you're going to have the limit as x approaches infinity and the limit as x approaches negative infinity. Okay? So then you ask yourself, as I go to the right, positive infinity, as I go to the right, what is happening to my curve? Positive infinity. How about as I go to the left? Negative. So this one isn't up, this one is a down up. Right starts down, ends up. All right, we're going to do a couple more pictures. The reciprocal function. The reciprocal function is this. That's the reciprocal function, the equation of the reciprocal function. This is the picture. It has a vertical asymptote at x equals 0. It has a horizontal asymptote at y equals 0. And then it's like a little hyperbolic quadrants 1 and 2. So that is a picture of the reciprocal function. The square root function. This is the square root function, and yes, indeed, it has a dot at the origin, and it goes up and out, just like that. Make sure it's curving that way, not this way. This is wrong. It's curving up and out. And our last one of the day, the exponential function. The equation of the exponential is e to the x power. The e does not stand for exponential, although that can help you remember it. The e actually stands for the man who first wrote about the number. His name was Leonard Euler. It starts with an E, so it's called Euler's constant. The picture of the exponential has an asymptote at the x-axis, an intercept at 1, and it goes up this space. Like that. You've heard people in the news talk about the national debt growing exponentially. That means
As we come into the end of the day, let us pray, Holy God, and cathedral tradition. In the name of the Father, Son, Holy Spirit. Hail the God,
our only hope.
which are alleviating